Hi, my name is Yaroslav Halchenko and I'm really glad to present to you today our project which we developed together with Michael Hanke from Germany, or we are still developing with Michael Hanke. Datasets, Decentralized Data Distribution for Consumption and Sharing of Scientific Datasets. Maybe the title is slightly different from what we initially proposed, but I think it better captures what the project is about, and I hope you'll enjoy it. You might also know us from work on other projects such as PyMVPA and Neurodebian. Altogether, you could find more about these and other projects from the Center for Open Neuroscience website, on which we also list other participants for these and other projects. And before I describe what Datasets is about, I would be really glad to acknowledge contributions and work of others on the team. Jason, Dibanjum, and Gergana, they worked on the project in the past and made quite significant contributions which made it better. Then we have Ben, who has been with us already for many years and tirelessly been working to improve and enhance Datasets, and Alex recently joined us. And the website you'll shortly see is the product of his work. Probably I don't need to present more of Michael Hanke, with whom we push together Datasets and other projects. And the acknowledgement will not be complete if I don't talk about Joy. Joy is the original developer of GitAnnex, the tool which we heavily rely on, but also is known for his paramount work in Debian distribution and on other tools which are really keen to many. And this project, it was supported by NSF and also Federal Ministry of Education of Germany. From Center for Open Neuroscience, you could also find links to other projects which you contribute in the scope of Datasets and other projects. So without further ado, I want first to actually give you a problem to tackle, or a statement which Datasets tries to address. So data is second-class citizen within software platforms. What that could potentially be. One of the aspects is, if you look how people distribute data nowadays, quite often you find that even large arrays of data are distributed in tarballs or zip files. Problems are multiple with these ways of distribution. If one file changes, you need to redistribute entire tarball, which might be gigabytes in size. And that's why partially we also couldn't just adopt technologies which are proven to work for software. And let's say in Debian we distribute complete packages, but again, the problem is the same. As long as you force wrapping all the data together in some big file, it wouldn't work, it wouldn't scale. Also, another problem is absent version of data. And many people actually underappreciate it and think that it doesn't actually exist or relates to their way of work. But no, actually this problem is quite generic. So if you look into this PhD comics caricature, you'll find that this probably relates to many ways how you deal with files, data, or documents. And you could see that actually how we tend to version our data is by providing quite often the date, right? Which creates some kind of linear progression, right? So we annotate that, oh, I've worked on these in those dates, but also maybe a little bit later, and we try to annotate it with some description of what was maybe done to the data, right? So in this case, it was a test run, then we tested again, then we calibrated, and then we ran into a problem, right? So all these kind of, you save the result of your work and annotate it, so later on you could either get back to the previous state. Let's say maybe you indeed made an error and you want to roll back, or maybe you want to just compare what have you done which broke your code or data, right? And as you could see, those messages could be quite descriptive. So what are the problems with the version? Oh, right. So, excuse me, not this one, this button. So but the problem is that version control systems which are created for code are inadequate for data, right? So the problem is quite often that it's duplication. You have copy of the data in the version control system inside somewhere, so you couldn't use it directly, but also it's present on your hard drive, so at least you have two copies quite often. Or maybe it's duplicated and just on a single server, right? And I could give you examples where data in a version control system filled up the version control system and meanwhile filling up the hard drive. And sometimes you try to commit new file and apparently you run out of space on the server and it might ruin your version control back on the server, rendering it impossible to get to the previous version. So you don't want to have that, right? Then another problem is that there were no generic data distributions, or at least there were no before Datalet. So there is no efficient ways to install and upgrade datasets. And when you also deal with different data hosting portals, you need to learn how to navigate them, right? You need to learn how you authenticate, which page you need to go to and what to download and how to download it. So just to get to that data set. And then maybe you get an announcement that data set was fixed and you need to repeat this over and over again, trying to remember how to deal with it. And I'm not talking even if a website became much better and slicker and changed all the ways how it actually deals with downloads from what it did before. Another aspect that data is rarely tested. So what does it mean for data to have bugs? Any derived data is a product of running a script or some kind of procedure on original data and generating new derived data. Quite prominent ones which you could find in references later on in this presentation is atlases. So atlases usually produced from the data running some really sophisticated script which generates new data, the atlas. And those atlases could be buggy. So how do you test the data? The same way as software. If we could establish this efficient process where we produce some data and verify that at least data meets the assumptions which we expect. If it's population or probability in the area which must be present in the entirety of population, then all probabilities should add up to 100 or nearby to 100. If it doesn't add up, then you have a bug. It's really simple assumption, but verifying that your data doesn't break those is really important, and unified way how we deal with data and the code could help to establish those data testing procedures. Also, it's quite difficult to share new or derived data. You've downloaded some data set from a well-known portal. How do you share it? What data could be shared? Where do you deposit it so people later on could download maybe original data and your derived data without even worrying that, oh, they need to get this piece from the original source and your derived data from another place. So how do we link those pieces together to make it convenient? That was quite a short of a talk. Somehow my slide presentation software decided that's enough. Okay. So what we're trying to achieve is to make managing of the data as easy as managing code and software. Is it possible? I hope that you'll see that it is so. And here is our new and flashy website, which we'll get back later. But I encourage you to remember this URL, datalet.org, and we'll go through it a little bit later in the presentation. So what Datalet is based on is on two pieces, and one of them is Git. I hope that everybody knows what Git is, but I'll give small presentation nevertheless. So Git is a version control system, and initially it was developed to manage Linux project code. If somebody doesn't know what Linux is, this is one of the most recognized and probably mostly used because it's used everywhere on the phones, on the servers, on the desktops, operating systems. It's free and open source, and it's developed in the open. And at some point, they needed new version control system which would scale for the demand of having lots of code managed there and many people working with it. So it's not a geeky project just for between few people. It is developed by hundreds, it's used by millions. What's great about Git is that it's distributed. So content is available across all copies of the repository. If you clone the repository, you have the entire history of the project, and you could get to any point in that development. You could compare different versions. You could do exactly the same things as original developers did on this repository. So it provides you as much flexibility to accomplish things locally without requiring any network access. And Git became a backbone for GitHub and other social coding portals. So GitHub came to fill the niche that there were no convenient online resource where people could easily share these repositories and work on them together. So Git is just a tool, and GitHub is just a web portal which provides you convenient, centralized management of the repositories and collaboration between people. But it's not a single one. There is other systems which use Git underneath, GitLab, Bitbucket. So it just creates the entire ecosystem of the tool and additional services and resources. What Git is great for is very efficient management of textual information, right? So if you manage code, text, configuration files, maybe some documentation or JSON files. So all of those are nicely managed by Git because it has really good mechanism to annotate the differences and compress that efficiently. So all those distributed copies are actually not that big. But the problem or inefficiency of Git is this exactly distributed nature of it, that it stores all the copies of the documents on all the systems, right? So if we have big files, then it becomes inefficient because now you will have two copies, right? You will have one on your hard drive, at least two copies, one on your hard drive, and then one committed into Git. And then if you push this into GitHub, you have again a big copy of that file somewhere, and anybody who clones that repository might wait for a while to just get it, and then they will might be a little bit upset because they wanted just one file from the repository and didn't care to download a gigabyte of data just to see it. So it's inefficient for storing data. What is the other tool we rely on is, as I said, written by Joy Has. It's Git Annex. So the idea was to build on top of Git to provide management for the data files without committing those files directly into Git. So Git Annex allows you to add data files under Git control without committing the content of the files into Git. And while playing with Git Annex and Datalet, you might see that files get replaced with a symlink. So what Git Annex commits into Git is actually just a symlink which points to the file which contains the data. This way you can commit really lightweight symlink and keep the data on a hard drive in a single copy, so it's not in a Git. And then what Git Annex does, it orchestrates the management of those files between different clones of the repository, or so-called other ways special remotes. But also it provides access to those files if they are, let's say, uploaded onto some website. So you have a URL. You could associate a URL with a file. You could upload it to FTP. You could upload it to WebDAV server. You could even get content through BitTorrent. Or you could use Amazon S3 storage as your container for the files. And it allows for custom extensions. Let's say you could offload data to Dropbox, Google Drive, Box.com, and many, many other data hosting providers. And Git Annex takes care also about avoiding the limitations of those platforms. Let's say Box.com for public account, it doesn't allow you to have files larger than, I believe, 100 megabytes. Git Annex will chop it up. So on the box.com, you'll have little pieces. You will not use them directly from box.com, but then Git Annex will reassemble the big file when it gets it onto your hard drive. So all those conveniences, and in addition, encryption. Let's say if you want to share some sensitive data and you cannot just upload it unencrypted to the public service, all those are provided by Git Annex. Also, additional feature which we don't use in the project is Git Annex Assistant, which is Dropbox-like synchronization mechanism. You could establish synchronization between your Git Annex repositories across multiple servers and configure them really flexibly, so you have, let's say, backup of all the data files on one server, and some other server will have only files which it cares about. Let's say data files. Another one might have only video files. Another one maybe just music files. Who knows? So flexibility is there, and it's all up to you to configure what you want where. In our project, we don't use it yet, but we do use it locally for synchronizing different Git Annex repositories. But another problem here, so we have really great two tools, Git and Git Annex, but both of them work on a single repository level. So to work in a Git repository, you need to go into that directory and accomplish whatever you want to do, right? It kind of doesn't go along well with the notion of distribution. You don't care where you are, you just want to, on your hard drive, right? So you just want to say, oh, search, find me something, install this, and give me access to this data, right? Or give me this file, even though maybe I'm not in that Git or Git Annex repository. Also, another kind of aspect, those are just tools. So similarly, like how GitHub provided convenient portal to the tool Git, we want to accomplish something where we use these tools, which are agnostic of domain of the data, let's say in your imaging, to give you guys access to those terabytes of publicly shared data already, which lives out there somewhere, so we don't need to collect it, we don't need to make copy of it locally, right? It's already there. So what we want to achieve is just to provide access to that data without mirroring it on our servers or without duplicating it elsewhere. And before going into demos, I want to give you kind of more illustrative maybe demo of what is data lifecycle here of data which we provide by Datalet. Let's imagine that we have a data set which comes initially from OpenFMRI, right? And lives somewhere in the cloud or on data hosting portal. Actually, we have two copies of the data. One of them might be in the tarball, somewhere on HTTP server, right? And another one might be extracted from the tarball somewhere on the cloud, which might have HTTP access, might have S3 access, but the point is that data is there. And then we have a data user, and that's us, right? Me, you, everybody who wants to use this data. So now options are we either go download the tarball, extract it, or we learn how to use S3 and go and install some tool, browse S3 bucket, download those files. But what we are trying to establish here is actually a middle layer, right? So we want to provide data distribution, which might be hosted somewhere. Maybe it's on GitHub, maybe on our server, where we'll take this data available online and we'll automatically crawl it. So here I mentioned this command crawl, which is one of the commands Datalet provides to automate monitoring of external resources. So we could get them into Git repositories. And actually you could see here that these greenish yellows, why you don't draw here, greenish yellow color, why you don't draw here? Here we go. So this greenish yellow color represents just a content reference instead of the actual content. That's why we could host it on GitHub or anywhere, because it doesn't have the actual data. So we collect those data sets into collections, which we might share, let's say the one which we share from datasets.datalet.org, right? And underneath we use Git modules, which is built-in mechanism within Git to organize these collections of multiple repositories while keeping track of versioning information, so you could get the entire collection, let's say, of OpenFMRI datasets for a specific date, for a specific version, if you want to reproduce somebody else's analysis. And then we are making it possible to install arbitrary number of those datasets via a unified interface. So here we mentioned command datalet install, which you'll see later, and hopefully those parameters like install into current dataset and get all the data will be less surprising. And also we provide shortcuts, so which I'll talk about later. But the point is that you could now easily install those datasets onto your local hard drive. And if you're doing some processing, you might add results of your processing. In this case, we've got new file, filtered bold file, which we could easily add into this repository, and which means we just commit it into the repository under Gitanix control. And later, we could publish this entirety of maybe collection of the datasets to multiple places. One of them might be GitHub, or we publish only the repository itself without actually data files. Again, those are just symlinks. And maybe upload the actual data to some server, which might be HTTP server, or some other server through some mechanism, right? But the point is the data goes somewhere, and the magic happens here thanks to the Gitanix, because that's the beast which keeps track of where each data file could be obtained from. So these red links point to the information of what Gitanix stores for us, that, oh, let's say this bold file is available from original web portal, right? It's available from a S3 bucket. It might be coming from a tarball. So that's one of the extensions we added to Gitanix to support extraction of the files from the tarball. And so it becomes really transparent to the user. And this new file, we published it there, so it might be available now through HTTP. So people who clone this repository would be able to get any file from original storage or from any derived data which we published on our website. So that's kind of the main idea behind Datalet. So altogether, Datalet allows you to manage multiple repositories organized into these super datasets, which are just collection of Git repositories, using standard Git submodules mechanism. It supports both Git and Gitanix repositories. So if you have just regular Git repositories where you don't want to add any data, it's perfectly fine. And we can crawl external online data resources and update Gitanix repositories upon changes. It seems to scale quite nicely because data stays with original data providers, so we don't need to increase the storage on our server. And we could use maybe, or you could use, because anybody could use Datalet to publish their collections of the datasets on GitHub and maybe uploading data itself to portals like box.com or Dropbox. And what happens now that we have unified access to data regardless of its origin, right? You don't care if data comes from OpenFMRI or CRCNS. The only difference might be that you need to authenticate. Let's say CRCNS doesn't allow download without authentication, so Datalet will ask you for credentials, which it will store locally on the hard drive. Nothing is shared with us. And later on, when you need to get more data, it just will use those credentials to authenticate on your behalf to CRCNS, download those tarballs, extract it for you, so you don't need to worry about that. And also we take care about serialization. So if original website distributes only tarballs, we download tarballs for you, extract them, and again, you don't need to worry how the data is actually serialized by original data provider. What we do on top is we aggregate metadata. What metadata is a data about data. So let's say you have a data set which contains the data. There is also information about what this data set is about, what its name, what its authors, what might be the license if it's applicable. So any additional information about the data constitutes metadata. What we do in Datalet, we aggregate metadata which we find about original data sets and provide you a convenient interface so you could search across all of it, across all the data sets which we already integrated in Datalet. And I hope you'll see the demonstration quite appealing later on. And then DataLad, after you consumed, added, extended datasets, or just created from scratch, you could share original or derived datasets publicly, as I mentioned, or internally. You could always publish them locally via SSH, maybe to collaborate with somebody, and that's what we do regularly. And meanwhile, we could keep data available elsewhere. Or you could even share the dataset without sharing the data, which is quite keen as a demonstration of good intent when you are about to publish the paper. That's what we did with our recent submission. We published the dataset, but not with the entirety of the dataset, but just with first subject. So reviewers could verify that there is good quality data, that they could get access to it, right? And that the entirety of data is in principle available, and it was processed accordingly, because the entire Git history is maintained and shared, but the data files are not. Okay, and the additional benefit, some of it which is work in progress, you could export the datasets. If you want to share just the data itself, you could export the dataset in current version in a tarball and give it to somebody. But more exciting feature we've been working on is exporting into some metadata heavy data formats. If you are to publish in scientific data, you will be asked to fill out a big spreadsheet, which is called ISATAB, to annotate metadata for your dataset. It's really tedious and an unpleasant job. But the beauty is that all that information is contained within metadata of either a dataset or of Git-Annex. So we could automatically export majority of information for you, so you just need to fill out left out information and be done. Our tools, or DataLad, comes with the both command line interface, which I'll use for demonstrations today, and with identical Python interface. So you could use them both in command line and while programming in Python. Python interface also comes with additional handy modes like Automagic.io and others, which we'll not cover in this demonstration, but you might find more about it in our documentation. Okay, so far, while working in DataLad, we covered already over 10 terabytes of neuroimaging, primarily data, and 10 terabytes is just what is the current version. So it excludes how much total of data files we actually cover, which probably times more. Let's say OpenFMRI releases multiple versions for the datasets as, let's say, bits format gets more refined more and more derived data added, new versions of datasets come out, and our datasets monitor all of those versions. So if you want to get previous version, they're all there, and they add up more to these 10 terabytes. But actually, locally on our server, we host only around 100 gigabytes, which primarily from the studies which we shared locally. So the rest, it comes just from the web. And so far, we covered OpenFMRI, CRCNS, 1 or 2 datasets from Kaggle, Indie Initiative, Functional Connectome, and even there is some music from Red Hole Radio archive podcast, which is quite nice, and it's shared on GitHub. We don't have it, I believe, as part of our datasets at datalad.org. And what is coming, Human Connectome project, any other dataset from XNet, data servers, and we are working on enhancing metadata support for more intelligent and detailed queries. And if you have other data providers which you want to see in DataLad, file a new issue on GitHub. Don't get scared with number of issues on GitHub. This is how we work. We file them, we deal with them, and we have majority of them closed. So there is a huge number of open issues, but there is many more closed, and if you add a new one, it wouldn't hurt us. And we want to work more on integration with NeuroDebian, so you could just apt-get install any of those datasets with Open Science Foundation. web portal, so we could upload the data there. Zenodo, which is work in progress, there is already initial implementation. And there is another additional feature which is already built in HudiConf, and hopefully I'll demonstrate shortly, that you could get Datasets bitzified, which means they will be in this Brain Initiative data standard layout, straight from the scanner. So if you have Siemens scanner, it's guaranteed to work, because that's what we do here at Dartmouth. All the data sets get into bits under Datalet control straight from the scanner. So you could immediately run bits applications of them. You could immediately start sharing them within your infrastructure for efficient processing. It opens many possibilities. Okay, it seems to be it is demo time. And before I actually give any demo, I want to familiarize you with our new website at datalet.org. On top you could see navigation for among major portions of the website. One of them is About page, which just describes the purpose of the Datalet and provides information about funding agencies and involved institutions. Next link is Get Datalet, which describes how to install Datalet. The easiest installation is if you are using your Debian already. Then it's just apt-get install Datalet command, or you could find it in Package Manager and install it within seconds. Alternatively, if you are on OS X or any other operating system, Windows support is initial, but it should work in the basic set of features. You have to install Gitanix by going to Gitanix website and go into install page, choosing the operating system of your choice and following the instructions there, how to get it. And after you installed Gitanix, you just need to install Datalet from Python package index through pip install Datalet command. Next page is features page, which is actually led to by those pretty boxes on the main page. And this page we'll go through later in greater detail. Another interesting page is Datasets, which presents you our ultimate official distribution, which points to datasets.datalet.org, which is the collection of datasets which already pre-crawled for you, and that's where we provide those datasets like for OpenFMRI, CRCNS, HDHD, and many others. Let me just briefly describe you the feature set of this basic website and mention that such websites, if you have any HTTP server available somewhere, maybe an institution provides, because you will not host the data actually here, or you don't have to. You could upload similar views of your datasets pretty much anywhere where you could host a website. And OpenFMRI, let's say we go to OpenFMRI, it lists all those datasets which we crawled from OpenFMRI. You could see also immediately mentioning of the version here, and version goes from what version OpenFMRI gave it, but also with additional indices pointing to exact commit within our Git repository, identifying that version. Another neat feature here is immediate search. So you could start typing, I don't know if you're interested in resting state. So here we go. It goes pretty fast and limits the view only to the data sets where metadata mentions this word. Let's say, let's look for Hexby. Here we go. Or let's look for movie. Here we go. So you could quickly identify the datasets by via browsing, and we'll see how we could do such actions later in the command line. And when you get to the dataset of interest, or it could be at any pretty much level, you'll see on the top the command which could be used to install this dataset, and describing some options. Let's say -r is to install this dataset with any possible sub-dataset in it recursively, -g to install it and also obtain all the data for it. And if you want to speed up the obtaining the data, you could use -J and specify the number of parallel downloads your server and bandwidth could allow you. Okay, let's go back to Datasets website. And another page on the website is development. So if you're interested to help and contribute datasets, provide patches, improve documentation, all of the development is made in open. We use GitHub intensively, we use Travis, we use CodeCov, we use read the docs for documentation. So, and that will be our next point. Documentation is hosted on docs.datalad.org, and it provides not yet as thorough documentation as we wanted, but some some documentation about major features of the dataset, or let's say comparison between Git, Gitanix, and Datalad. But it also provides really thorough interface documentation. So as I mentioned before, we have command line and Python interfaces. Both of those interfaces generated from the same code, so they should be pretty much identical. It's just depending on how you use command line or Python, it will be different. But otherwise, all the options, all the commands, they look exactly the same. And in command line reference, you could find all the documentation for all the commands. You could see that I have some popular ones in my case, right, where I went before, and it provides documentation of what those, and of course there is notes for power users, and quite elaborate documentation here about all the options which are available to the in those commands. Okay, so let's go back to features. And first of the demos, which I want to show you, will be about data discovery. We aggregate lots of metadata about datasets in Datasets, which allows us then to efficiently query available metadata about which datasets match desired criteria, right? All those demos on the website, they are equipped with screencasts, which if you click, they'll print the commands and actually comments describing what I'm about to tell you interactively. So at some point you could go through them yourself and run those commands also on your computers. But meanwhile, let's just get into the terminal where we'll go through this data discovery demo interactively. So once again, we could search for metadata. And in this example, we'll imagine that we are looking for some neuroimaging data where description mentions word radars. So we could type command datalad search radars neuroimaging. All commands in datalad, they are similar how in Git you specify Git and then command commit or fetch or pull. The same interface idea is adopted in datalad. So we use datalad, then we type command, and then provide arguments to the command. In this case, we'll run the command to search for data, right? And what happens first time you ever run datalad? It needs to install the super dataset, which you just saw when we browsed datasets.datalad.org. That's exactly the Git repository, which it will clone under your home directory. In my case, home was /demo, so Datalad offers me to install it on my behalf. What happens here, it goes, clones this super dataset, which we refer to as triple slashes resource identifier, to make it shorter. Otherwise, you could just type the install http://datasets.datalad.org to achieve the same effect. After it cloned it, which already happened, right, it needs to load and cache local metadata. So it takes all the metadata which is contained within the super dataset about all the sub-datasets which are present in it. So it didn't clone any sub-dataset. It cloned only super dataset, and it indexes all the metadata which it could find. So it usually takes a few seconds, and then after it's done, it will provide output for the query which we entered. So we were looking for radars neuroimaging. There we go. So at the end of the search, right, it provided us output that those datasets mention radars and neuroimaging somewhere within their metadata. So search by default searches within current dataset, right? But before we didn't have any data set. So if we just run the same command again, right, datalet search radars neuroimaging, and then it would offer us to search within the super dataset which we installed in the home directory. So I could say yes, search there, and then next search, you saw that it's quite fast. To avoid all these interactive questions, we'll just go inside the directory and we'll search. Oh no, not yet actually. So if you know within which installation of a dataset you want to search, you could specify it within -d option. As I said, all the commands, they have some kind of options, and -d usually is to specify which dataset to search with. And / again stays for our canonical distribution. So if it's used as URL, it will be http://datasets.datalet.org. If it's used as representation of which dataset locally to search within, it will be the one which is installed under your home directory. And in this case, we'll do another query. We'll search only within field author, and we'll report the finding not in terms of which path matched or which dataset matched, but we'll also report all the fields which provided this match, and we'll search for word hexp. As you could see, it did the search and it was quite quick, right? So for convenience now, finally, let's switch the directory so we didn't need to type this path or specify the dataset. So I just wanted to present that it's possible to specify a dataset where you're not under. So let's rerun the same command, I guess. And you could see that it goes and finds it quite quickly, and it reports author field because that's the only thing which we searched through, right? And it reports it, and all of those hits, they have hexp word in it. So instead of matching all matching fields, we could specify which fields to report actually. So let's say in this case, let's report not only the author, but also the name of the dataset, so we could find what kind of dataset that was about, right? So again, query runs relatively quickly and reports the fields which we want. So okay, enough of searching, let's install something. As you saw, by default, the command returns the paths to the datasets, right? So we could quickly install them. Let me clean up the screen so it's a little bit cleaner here and you could see vividly what I'm doing. Once again, if I go back and just remove this portion, this is pretty much what we've done before. We search for datasets which have author hexp. And